Now this so this f of x equal to f of x, where f of x is the ith coordinate of that this tuple. Now this pi, it's the projection map from the product space to its ith coordinate space, that's I, and they are continuous. Their projection mappings are continuous mappings. Now let's verify this. Pi f is equal to fi. The composition of pi and f is equal to fi. So let's verify this first. So since this f is a function from x to p, so f of x belongs to p. So let's find this pi f of x, because we have to verify these two functions are equal. So we need to verify that they are equal at each point. Both are the functions on x. The domain of the function is x. Pi f, its domain is x. Fi, the domain of fi is also x. So let us find this pi f of x. Since f is a function from x to p, so f of x belongs to the product space, and pi of f of x, where f of x is an element of product space, so pi of f of x means its ith coordinate, that's equal to fi x. So that means pi f is equal to fi for each x. Also, since pi and fi, they are continuous, therefore f is continuous function. Now since x is completely regular space, so that means therefore for each x, so this if we know that for a completely regular space, the set of continuous and bounded real world functions c of x are, it separates the points of x. Separates the points of x means that given any x and y in x with x not equal to y, there is a function in cxr. Let me denote that function by fi, because we have indexed the elements of cxr by these fi's. So this fi, there is some function fi in cxr such that fi(x) is not equal to fi(y). So now let's define this the function that f from x to the product space by defined by f of x equal to the fi(x). Here this function f of x equal to fi(x), it will be then 1 1, because for x not equal to y, there is at least one coordinate where fi(x) is not equal to fi(y). Therefore this tuple fi(x) tuple is not equal to fi(y) tuple. So that means the function is 1 1. Whenever x is not equal to y, the images are not equal. So that function is 1 1. So this means that so f from x to p is 1 1. So that means f of x that means this x is embedded in p. X is embedded in p as a set, as a set. So or you can see this the cardinality of x is same as cardinality of f of x as sets. They are same actually in terms of cardinality, but we show that this x is embedded in p as a topological space. So that means we need to show that x and f of x, they are same as topological spaces. That's what we need to verify. Okay. So to verify this, they are same. This x is embedded in P as a topological space. We first observe that actually we need to verify that this x is a subspace of P as a topological space. Actually, f of x is we need to show that f of x is a topological space of P as a subspace of P as a topological space. Okay. Now we have two topologies on X actually. One as its own topology. So there are two topologies on X. There are two topologies on X. One as its own topology, and second, X as its own topology, and second when we treat it as a subspace of second and second is the relative topology, because X and f of X, they are same as the sets, so we have two topologies on X actually. One as its own topology because X is a topological space, and second by treating as a subset of P. So it has a relative topology. Okay, so its own topology and one of its relative topology, which is as a subspace of relative topology, which is as a subspace of P, Now, since this f is continuous, since f from X to P is continuous, it's a continuous map. So it means that it's a continuous map. Therefore, the given topology on X, is stronger than the relative topology, on X, because given topology of X makes this f continuous function, and relative topology is actually the smallest topology, because this relative, as when we talk about the relative topology, then we have to treat X as a subset of P. So when X as a subset of P, so that relative topology means the smallest topologies, actually it's the smallest topology on that subset, which makes each projection continuous. Actually, the restrictions of each projection on that subset makes continuous. So this means this topology, which is a given topology on X, is always stronger than the relative topology. On X. Now, second, this CXR. What's CXR? By treating X as a subset of P, CXR is actually CXR is precisely the set of CXR is precisely the set of CXR is precisely the set of all restrictions, it's a set of all restrictions to X, set of all restrictions to X of projections or restrictions of projections, set of all restrictions of projections Pi, which are projections of P, actually projections of P onto its coordinate spaces, onto its coordinate spaces I. Okay. By treating X as a subset of P, actually what are CXR? CXR is actually the collection of all continuous and bounded functions, real valued bounded functions on X. But by treating X as a subset of P, then CXR is actually the set of all restrictions to X of projections of P, because Pi is a projection on P. So let's I will take the restriction of Pi on to this X. So it will be it precisely the set of all restrictions is the set of all restrictions of x restrictions to x of all projections pi of p onto its coordinate space. This is pi onto its coordinate spaces pi. Okay, because projections are the mappings from p to the coordinate space I, and this x is treated as a subset of p. Then these projections on x, they are actually the restrictions of those projections pi of p onto x. Okay, so they are actually they are precisely the restrictions. So this is very important. They are actually restrictions here. They are actually restrictions here. Second thing is that they are actually restrictions here. Now, since x is completely regular, since x is, it's given that completely regular space, completely regular space. Since x is completely regular space, therefore by fact 1, for completely regular space, by fact 1, its given topology, it is given topology, its given topology is equal to the weak topology, is equal to the weak topology generated by, that's fact 1 actually, generated by CXR, by fact 1. Since x is completely regular space, therefore by fact 1 its given topology is precisely equal to the weak topology generated by CXR. But this CXR is actually, it's precisely the set of all restrictions on to x of a set of all restrictions of projection maps pi to x. Okay, it's actually this we have already seen that C of xr is actually the set of all restrictions to x of all projections pi of p onto its coordinate space I. That's already explained in the previous page. Now this is actually the set of all restrictions of projections. Okay, so now by statement 2, now by fact 2, what's fact 2 actually? Fact 2 states that if we have a subspace of a given product space, so now this can be treated as a subspace of, this can be treated as CXR. It's the set of all, it's a projections actually, which makes projection is continuous. It's actually the set of all restrictions to x, all restrictions to x of projections pi of p onto its coordinate space C of xr. It's that. By statement by fact 2, the given topology on x equals to relative topology. Is equals to the relative topology on x by treating it as a subset of p. Now here by statement 1, the given topology is equal to the weak topology generated by CXR, and the weak topology generated by CXR is same as the actually relative topology here, relative topology on x, because this CXR is actually, what's it actually? It's actually the all set of all restrictions to X, restrictions to X, because X is treated as a subset of P. Restrictions to X of projections Pi of P onto its coordinate space I. So therefore this X is a subspace of, that's very important, it's actually subspace of P. That's what we need to show actually, it's a subspace of P. First we have seen that it's a subset of P as a set, because this cardinality of X is same as cardinality of f of X, and f of X is subset of P. So as a set, it's a subset. First we have seen that this. Now actually it's not only a subset of P as a set, it is also a subspace of P, because its topology, given topology, is equal to the same as a related topology on X. So that means X is a subspace of P. X is a subspace of P. X is a subspace of P. Okay. So let's take let's take exclusion. X is subset of exclusion, which is subset of again P. So this P is a compact Hausdorff space. X is subset of exclusion and exclusion is subset of P. So that means X is dense in what? X is dense in exclusion. And what's exclusion? Exclusion is a subspace of the compact Hausdorff space. Therefore exclusion, X is dense in exclusion, and exclusion is compact, it's compact Hausdorff space. Exclusion is compact Hausdorff space. Exclusion is compact Hausdorff space. So that means X can be embedded in a compact Hausdorff space such that X is dense in that compact Hausdorff space. So or I can say that X is embedded as a dense subspace of compact Hausdorff space. X is embedded into a compact X is embedded as a dense subspace of a compact Hausdorff space. X is embedded as a dense subspace of compact Hausdorff space. So this is the first part that we need to verify, that X is embedded as a dense subspace of a compact Hausdorff space. Now we show that every bounded continuous function on X can be extended to a bounded continuous function on X closure. So that's again simple actually. Okay, so this is again we need to show that every bounded continuous function on X has a unique extension to a bounded continuous function on X closure. Okay. Now this is again simple actually, because each now let fi belongs to CXR. So it's a bounded continuous function on X. So this fi is actually, it is equal to restriction of Pi on X. It's like this. Now what's the extension actually? What's the extension actually here? The extension of fi to X closure is actually the restriction of Pi to X closure. Because what are Pi's actually? They are mappings from P to II, and X closure is subset of P. So that means actually this the extension, if I will denote extension of fi extension, let me denote this extension of fi by fi, extension fi dash of fi. Extension fi dash of fi to exclusion is actually the restriction of pi to x. Why it's restriction? Because this pi, it's a map from p to pi, and exclusion is subset of p. So let's write this fi dash is actually the restriction of pi to that subspace. Sorry. And then it's trivial that fi is same as fi dash on x, because both fi and fi dash, they are both are actually the restrictions of pi. Fi is the restriction of pi to x space, because x is also a subset of p, and fi dash is the restriction of pi to exclusion. And this fi dash is again, it's a bounded continuous function, bounded continuous real function. Fi is also a bounded continuous real function. So that means every bounded continuous real function on x can be extended to a bounded continuous real function on exclusion, and that exclusion is actually it's a compact Hausdorff space. So thus we have proved that we have proved this theorem. If x is a completely regular space, then there exists a compact Hausdorff space Bx with the following properties. With the following properties. What are those properties actually? Let me see. Have the following properties. X is dense as a subspace of Bx. This Bx actually here exclusion that we have seen in our proof. Exclusion is equal to Bx. And every bounded continuous real function on x has a unique extension to a bounded continuous real function on beta x. Beta x is actually exclusion. Okay, so this proves the theorem that Stone-Cech compactification theorem. Stone-Cech compactification theorem is proved completely. Then it has also a complex version that you can easily verify that complex version. So where you have to take the continuous bounded functions from x to c set of complex numbers, and you will see that every complex bounded function, bounded continuous function on x can be uniquely extended to a complex bounded function on exclusion, where exclusion is the compact Hausdorff space containing x as a dense subspace. Thank you.